but he just gonna go in the background. I don't think he went. Okay, good. So I'm gonna go to the sharing. Just one more minute. I don't know if anybody else of the team members. We have a lot of people that do the seminar series. It's on me. There on paper, but that's okay. Coming at this exact moment. Oh, sorry. I go with my iPhone. Okay. We start on the dot. So let me start. So welcome back again, everybody, to the online SPICE-SPIN+X seminars. I'm Javier Sinova, the director of SPICE, and we do this jointly and in collaboration with Libor Schmekial, now at Max Planck Institute in Dresden, leading his own group, Angela Wittmann here in Mainz, Karin Evershaw, Sitte in Duisburg, and in collaboration with the SPIN+X SFB, led by Martina Schliemann and Burkhard Hillebrands in Kaiserslautern, and Matthias Chloe here in Mainz. This is a Zoom webinar, as you know. So please raise your hand or in the chat if you're allowed to actually ask your questions, and I will pass you or promote you afterwards to the panel to ask the questions directly to the speaker, in this case, Hans. And then if not, I can ask it for you if you cannot have audio. We now just begin. This is the first one of the season of this fall. But then please check the seminar and also make suggestions if you like to give a seminar or have a good speaker that you think could give a seminar to send it directly to me. Today is a very good old friend, Hans Huebl. He's a scientist at Walter Meissner Institute in Munich, and also at Technical University in Munich. And he did his habilitation to Munich. So he's a Munich guy, he's a Bayern guy, as Bayern as he gets. But he's well known in our field for these hybrid systems that he studies in the relation of quantum sensing and quantum communication and quantum computing in the context of spin physics, particularly in the spin currents and magnetic transport at the nanoscale, to creating some device physics that has been very fascinating through the community. There are several awards, but I just highlight two of them here, which is the Academy Prize from the Carl Tiermich Foundation for the Promotion of Young Talent, and the APA Standing Fellow. And I also know that he also gives excellent talks. So with this, I am just simply going to let you please share your screen and Hans, and start your seminar whenever you are ready. And I will to mute myself here and to give you more broadband here. Okay.
Yeah, thank you for inviting me, Jairo, and thank you for your kind introduction. It's a pleasure and an honor to have this opening seminar, and I'm happy to present to you today what fascinates me in the terms of connecting quantum systems, or in particular today, spin excitations and resonators. And I will kind of come to various types of resonators that we are investigating presently, and tell you a little bit about what the ideas behind these resonators are. To begin with, I would like to thank the funding organizations who support this work financially. So this is the German Science Foundation in terms of via the Clubs of Excellence, the Munich Center for Quantum Science and Technology, and Transregio, the Transregio TRR 360. And there's also funding coming from the BMBF, that's the Federal Ministry for Science and Education, and there is a grant challenge for quantum communication which funds parts of this work. I'm super happy to work with all the peoples that you see here on this acknowledgement slide, and it is really a rich and stimulating crowd which really helps each other out, kind of bounces ideas off each other, and I think this really drives us forward with combining the science with personal interactions and super beautiful discussions. So there's Sylvia Viola Kosminski's group from formerly Max Planck, now RWTH Aachen, who we often ask for help in theory. There's Garrett Bauer's group, who is traditionally delocalized over several continents. There's Stefan Rotter's group at TU Vienna, and from an experimental perspective, I'm collaborating with Sebastian Gönnwein's from Constance, and we try to bang our heads together from time to time to come up with new ideas. Last but not least, I want to acknowledge the PhDs and the helping hands and all the scientists at the WMI. The PhDs, today I will kind of present work from Manuel Müller, Patricia, Stefan, Johannes, and Florian. But of course, this is building on greater efforts, and we will come to that in a bit. And there, the WMI is basically a unique place where you can play around with magnetism and quantum science, and I would kind of like to show you today a part of what's under the hood there. So this is, I think, a very personal slide. What is my motivation behind combining quantum systems, or what CIS promises? I started with basically the question, can we see individual excitations in solid-state systems? Can we see individual magnons? And now it kind of goes more into the direction, can we understand more about the ground state, more about the excitations? So what would be nice probes of entanglement? Or can we imprint artificially something new by combining several forms of excitations? So you see here, I think, a very seminal example from the Nakamura group, and we contributed here into this field quite a bit, I think, where you see an interaction of a ferromagnetic resonance here, which would run diagonal with a microwave cavity, and there you create a new form of a state, a hybridized state, and this is actually part of the theme I would like to guide you through today. Then there is, in these hybrid excitations, the question is, how do they propagate? We're talking about magnetization dynamics, so there's an angular momentum property connected to the magnetization dynamics. How does this evolve in hybridized systems? These types of questions I'm interested in. This, I think, nicely also links to quantum science and technology questions, which are anchored in sensing applications. Can we store information elegantly in solid-state excitations, or can we build transducers, or these sorts of questions? I think spins or magnetic excitations are super rich in this perspective because they come in multiple flavors. You can think about any ordered magnetic phase, or you can think about paramagnetic spins and paramagnetic state. And so there's a lot to do there, and I think they all have their own rights to be investigated. Paramagnetic systems typically come along with coherence times which are extended. You can think about magnetic phases. I think there it links nice to alternative integration schemes. Alternative to microwave spectroscopy, where you can think about probing the magnetic excitation by spin Hall physics or by optical means. And another neat feature, so to say, is these magnetic systems are typically nicely integratable in electronic circuits. I think there are multiple classical examples, but I think there are also quantum examples in this respect. So one of my motivations, or I think of general of the motivations of the field, is to think about what can we learn about the quantum state. Is there entanglement in this ground state, etc. And for me, there are kind of overarchingly or rudimentally speaking two approaches. You can either think about getting a probe, measure susceptibility, measure a signature, and then compare this with theory. And what I have there in mind is typically quantum critical points, and then look at mode softening or ideas in this direction. Or and there the hybrid systems come into play. The question is, can we build this out of building blocks? So can we create a situation where we, in an engineered fashion, want to probe or imprint quantum state in a magnetic excitations or any solid state excitations by coupling it to an auxiliary system? So what do I mean with this? So many of you might know that you can construct quantum states, microwave quantum states, for example, by combining superconducting qubits with microwave resonators to quantum circuits. And then you can think about taking this bundle and connecting this to a spin system for probing the quantumness of this magnetic excitation, for example. And the Nakamura work would be one of these examples. And what I want to present you today is basically our road into these directions, and give you some hopefully stimulate some ideas, and tell you a little bit where we stand and where we are going, and what our next steps are. So, and therefore I group today's presentations in two sections. One is concerned with the interaction of spins with microwave photons, and I call this typically spin-photon hybrids or Magnon-phonon hybrids. And the more new kid on the block is connecting magnons to phonons in these bulk acoustic resonator type of devices. However, I would like to kind of show you the embarrassingly simplified picture of what I need in terms of magnetization dynamics. And I just want to remind you of the classical equation of motion. So you take the magnetization, and in a magnetic field, this magnetization vector will precess. This can be stated. It's a good statement, I think, for magnetically ordered systems as well as paramagnetic systems. And you can control the angle between this magnetization and the effective magnetic field or the applied magnetic field by using a generalized drive. So one of them would be, or a typical scenario would be, a microwave drive, which co-propagates or co-oscillates with the Lama precession frequency, which is the rotation frequency of this precession frequency of this magnetization vector. And this is an established concept. So you see here the initial citations, and it was developed already in the 40s from a classical perspective as well as a quantum perspective. And so what's new, so to say, new in the sense of connecting this to a different type of systems, is to make use of this precessing dynamic magnetic dipole. So we take this red arrow here as the dynamic magnetic dipole, which is the a projection on the plane where the H field is normal to, and this precesses here along this gray line. And the idea is now that this magnetic dipole can radiate an electromagnetic field. And now the idea is that you take a resonator of some kind, and this is resonant with the Lambda precession frequency, so you can capture the emitted electromagnetic field. And then you design it that this electromagnetic field is not lost, but it's kind of radiated back onto this magnetization dynamic system, and therefore you can induce a coupling rate. And it turns out that this was initially pushed forward by Tevis and Cummings. And technically for us, the difficulty is typically the engineering of this electromagnetic field. So to give you an idea, what people state is G0 in terms of a single spin coupling, and then together with the ensemble of spins, so there are n spins in this ensemble, this coupling rate is boosted from around about 50 to 100 hertz in typical superconducting resonator structure to megahertz scales. And you can state this in terms of n, in terms of the number of spins or the spin density rho, and this eta is a so-called filling factor, which accounts for the fact that the mode of this microwave resonator is finite, and the best you can do is you can basically fill this mode up to 100%. The typical modeling of this scenario is that you say your microwave resonator is a harmonic oscillator, and your spin system can be modeled as a harmonic oscillator as well. And you assume here that you are in a low excitation regime, and this allows you to live under this approximation. And then you say, okay, now I have to describe the coupling between the two entities, between these two harmonic oscillators. And you say, I'm annihilating an excitation in the microwave magnetic field, and I create it in the spin system, or vice versa. And I decorate this, simply speaking, with an effective or collective coupling rate. And this makes the description rather general. There's a lot of details hidden in this effective coupling rate. There is the nature of the coupling. So we talked about magnetic dipole coupling in the previous slide. There's a mode overlap coming in here, and this can get rather intricate, what you understand here. The classical analog of this Hamiltonian is depicted here. So you have the blue pendulum, for example, representing your microwave excitation. The green one, the spin excitation, and the effective coupling is here denoted by this spring. And if you're really in this situation that is depicted here, then you can transfer excitations from the microwave to the spin system and vice versa. But you implicitly feel that there are kind of some constraints if you depict this model, because you're assuming here intuitively that the damping rates of the individual pendula are weak. And this, if you assume this, and this is the so-called strong coupling regime, then you have basically this normal mode system that you know from your undergrad mechanics course. What people then define as a figure of merit is a cooperativity, and this cooperativity compares quantitatively this coupling rate with the loss rates. I want to kind of note here that this is not the only definition, and the definition actually depends on your viewpoint. So there's a quantum version of this, or this is the classical definition of cooperativity. So there are various cooperativities out in the field, and they have then in the end different meanings. So then you can ask the question, so strong coupling, when do I have strong coupling, and how does this link to cooperativity? This is already so slightly hinted for in this this plot here. This is from the Hong Tang group. There's a strong coupling regime, there's a weak coupling regime. These are the trivial ones. And then there are kind of additional regimes. There's a Purcell-enhanced regime, a Magnon-induced transparency regime, and this really relates to the ratio of the coupling rates to the loss rates. And I want to spend the time today to show you a little bit, or kind of introduce you to the signatures, and also want to underline slightly that the cooperativity larger one is not synonymous for strong coupling, and just give you some examples. So this is the prototypical strong coupling case. So what do I assume here? So I assume here that a microwave is incident on a microwave resonator. In this microwave resonator, there is a spin ensemble. And we now basically play around with the coupling rates, the input coupling, the loss rates, or the total loss rates of the systems, and this effective coupling rate. And if this collective coupling rate dominates everything, then you see this beautiful anti-crossing, which tells you that you have a state hybridization, and that you mix basically the characters of the microwave excitation and the spin excitation. What this mixing means might be different for the respective excitations, but you can basically define here mixing ratios. Then you have the weak coupling regime. For this transmission resonator, you almost see nothing here. We will come to that in a minute. For the Purcell-enhanced regime, you can basically see that this resonator is overdamped in the intersection in the resonant case with the spin system. And then here in the transparency regime or absorption regime, you can see here kind of a tiny little feature wandering through. And I'm magnifying this for you because otherwise it's super hard to see. So you see that basically you have this line here crossing the microwave resonator. The damping of your spin system is here very, very weak. And this appears in this transmission type resonator as a dip in your resonance structure. And people would call so this comes from quantum optics, then that an induced absorption feature, for example. The weak coupling, that's what you pursue for microwave spectroscopy experiments or ferromagnetic resonance experiments. You see here this slight dimple here, which is only a minimalistic modification of the transmission of the microwave resonator, and this is results only into a weak disturbance of your microwave of your spin resonance, and this therefore you can use this to analyze, for example, line widths or the damping of your magnetic system. Okay. Then I want to mention that spins and resonators is in the meanwhile a very broad field, which is partially disconnected. And the key is basically that people approach this from different angles. So if you're more into quantum sensing, or quantum information storage, then you would naturally prefer paramagnetic spin ensembles, and that is connected to the coherence times of this paramagnetic spin ensembles. The magnetically ordered spin ensembles have basically a different flavor, so you gain a lot in coupling compared to a paramagnetic systems, because you can crudely estimate that you have one Bohr magneton per lattice per atom in your system. So you have huge densities. You can interrogate the magnetic system in a different fashion. So I mentioned the spin Hall effect or optical concepts. and this kind of brings this into a different regime. And so if you would make me put labels here, so these are kind of the more the storage and quantum sensing community, while here you think about large cooperativities, can we build transduction concepts out of these systems. To give you some idea how this looks in experiment, I brought along an experimental example. So we pack our paramagnetic spin system, it's phosphorus dopants and silicon, in a microwave cavity, and we will have a quick look what's going to happen and what are the characteristics of the systems. In order to do this, I want to introduce to you the microwave resonators, and we favor, for various reasons, superconducting planar microwave resonators. First of all, we can engineer them quite nicely. They have the neat property that they have low damping or ultra high Qs. And then you can also quite neatly confine the electromagnetic field, which is kind of captured in this microwave resonator to small volumes, and that gives you at the end a so-called large B1 field in vacuum fluctuations. They come in two flavors. You have this lumped element version where you have this meandering inductance combined with a capacitance. So just think about this like an LC resonator. Or you have a more distributed systems in terms of a coplanar waveguide, and it really depends on your experimental situation, what you will prefer in the end. We looked into various material systems, and in particular niobium and niobium tinitride are for us preferable because they sustain larger magnetic fields, and the high Q factors survive in moderate magnetic fields, and I mean something like 100, 200, 300 millitesla for in-plane magnetic fields. So the evanescent field, or the field which is contained in this microwave resonator, so you see this here for this type. You have here a cut along the vertical axis, and you can calculate the microwave B1 field, so the microwave excitation field, which is usable for your spin excitations. And what you see is due to the alternating current directions here, you can nicely confine your electromagnetic field to the surface. And then you can place crystals of suitable dimensions and geometries nicely onto the surface. This is relatively low tech for us, and you reach a large filling factor eta. So that is basically the trick, and this is one part of getting decent effective coupling rates. You pack this system into a cryostat. It is not required to use a dilution fridge. So this is an example with a dilution fridge, and to give you some dimensions, so this would be the length of this shield here would be half a meter or so. There you see an electromagnet, and basically the idea is that you have some microwave circuitry which is in this dilution fridge, which protects the device under test, or the coupled spin-photon system, from the environment, so that it's not excited, or that you can prepare it in a quantum ground state, and then you carefully amplify your signals which are coming out of there, because they might be on the level of single microwave photons. You use, or we use, typically for these studies, continuous wave excitations. So we measure our spectroscopy signal with a vector network analyzer, and we can also do pulse excitation for doing pulse echo sequences with a pulse generation system and a time domain detection system. So the example I brought you with me is a silicon sample. It's a silicon-28 sample, so it's nuclear engineered. The that means that the nuclear spins in the silicon are artificially removed. There is phosphorus donors in there, which substitutionally replace one of the silicon atoms. This has an extra electron, and this extra electron is captured at this donor site at low temperatures. The electron has an S equal 1/2. The nuclear spin is also equals 1/2, and this is the way of how you would describe the so-called spin Hamiltonian or the spin properties of this system. And the signature that is kind of the fingerprint of this transition are two transitions which are separated by 4.2 millitesla. And this is what I want to show you. So this is the spectroscopy. So this is the transmission through the system. You see here the dip in the transmission, microwave transmission originating from the resonator. And then we subsequently step this frequency traces for different magnetic fields. And if you follow then the resonance frequency, you see here a beautiful anti-crossing. And if you analyze this two-dimensional data set, you can determine all the parameters that you require. So this is an example of the strong coupling regime with a cooperativity, for example, of 13. You can do pulsed excitations. So this is interesting when you are interested in quantum measurement protocols. So the Hahn echo sequences here are one of the workhorses. You have a coherence time of 6 milliseconds. So this corresponds, if you can extrapolate a magnetic field sensitivity of roughly 10 femtotesla per square root hertz. The sensitivity that you see here in the spectrum is roughly 10 to the 5 spins per square root hertz. So this are the rough numbers which are associated with this detection scheme. What's nice and what was very impressive for me personally when I started this is so these are time traces, and these time traces record the echo of the Hahn echo. And typically, if you are doing electron spin resonance, you average here over 10 to the 5 to 10 to the 6 echoes to get a decent signal to noise ratio. What we are doing is actually something different. So we are doing single shot experiments. We perform the sequence, record in a singular time trace this echo, and then we step to the next magnetic field. And you see here basically the echo of the hyperfine transition that I showed you earlier. There was one thing which really puzzled us for a while. You would naively, in your experiments, expect only the first echo. But evidently, so we have here, we operate here in the strong coupling regime. And there you notice experimentally that you see really a train of echoes, which actually beautiful signal to noise ratios. So it's not an artifact. And together with Stefan Rotter's group from the TU Vienna, we figured out that this has something to do that we actually perform some phase encoding in our spin system, and this results into a echo revivals, which was initially not expected here. So let me switch gears a bit. I showed you what you can do if you have spins with a microwave and connected to microwave photons. Actually, the same holds true. You can do similar physics with magnons and photons. I spare you here of the extended discussion and want to move a little bit to the new kid on the block. So there are magnons and phonons. And keep in mind, so the mindset is still that we are connecting to resonators, magnetization dynamics, and now an acoustic resonator. And this acoustic resonator is basically an elastic wave, which is a standing wave in this slab of magnetic thin film plus typically substrate. And this effective length of this acoustic resonator defines basically then the frequencies or the frequency comp of this acoustic resonator. You can't only do this. This concept was spearheaded actually by the Klein group from Grenoble. You can also think about different phononic excitations. So what could come to mind are surface acoustic waves. Manfred Albrecht is active. There are various groups in the US active in this direction. I think Matthias Weiler, during his PhD at the Walter Meissner, he also did some groundwork in this direction, where he looked into surface acoustic waves and how they interact with ferromagnetic resonance. So this is the alternative to this, and I'm convinced that you could construct here a surface acoustic wave resonator and then look at this coupling physics with ferromagnetic excitations. What I personally found a very, very nice experiment, because it combines the Magnon-phonon physics here, which is here's your microwave cavity, a Higgs sphere, with Magnon-phonon physics. Was this experiment? So this is from the Davis group in Canada, and they kind of engineered, or kind of they adjusted the coupling between the microwave cavity and the magnetic excitations in a way so that it matches the mechanical eigenfrequencies of the Higgs sphere, and they beautifully showed some tripartite physics in this system. Okay. However, again, I want to be slightly didactic and want to remind you how we typically think about phonons, in particular in the sense of bulk acoustic wave phonons. So if we open our textbook of choice, then we are typically confronted with pictures like this, where we think about phonons as lattice displacements, as a collective lattice displacement. And you have typically two choices. You have a longitudinal phonon, as depicted here, or a pressure wave, or you have shear wave phonons. And from this kind, you have two, because of the number of dimensions orthogonal to your propagation vector. You learn then pretty quickly that life is more complex. So this is an example for silicon. You can think about optical phonons as well. However, I remind you that our spin physics that we excite from an experimental perspective are tens of gigahertz. So we are sitting down here, and so we can constrain or reduce our discussion about the interaction of these magnetic excitations with the acoustical phonon branches of the crystal. The system, there's I think a beautiful paper by the Bauer group when they considered phonon pumping as an effect. And so their idea was that if you take precessing magnetization, and we have seen this already, that you assume that your magnet has some magnetoelastic properties, and that means that this a dynamic magnetization vector links to your stress vector in this thin film. This launches then phonons into this bulk, and this are captured here by a phonon thing where they are dissipated. And then in this spirit of effective coupling rate and mode overlap, you can think about when this process is becoming effective, and it turns out that this the effectiveness of the stamping process by the phonons is frequency independent. What it's neat in this respect, it gives us an ansatz of how to connect magnetization precession to phonons, and therefore we can think about there is some helicity. Can we transport angular momentum in this system, for example? Or actually, we have to think more carefully about the crystalline structure of this slab of substrate, for example, and think about phonon propagation velocities, and can muse if we can achieve something which is connected to phononic birefringence, which is the analog, or consider the analog of the optical birefringence effect. And if you're more, if you find your damping of your magnetic system more a nuisance, then you could also think that can I make use of this and kind of reduce the damping via resonant phonons in my systems by appropriately engineering this system. So these are the motivations, or these were the motivations for us to look into this. And of course, so I'm giving you, from my perspective, the very intuitive, try to give you the very intuitive picture of how this all works and why the magnetization is connected to the elastic properties of the crystal. So we are talking, or we are basically looking back at this multiferroic triangle. And at the end of the day, what we're interested in is the connection between the magnetization and the magnetization vector to the stress in the lattice. And so if you have a magnetoelastic system, so you need a magnetic film or magnetic material with magnetoelastic properties, then you find out that if you apply a magnetic field, you control the magnetization, and this basically tries, that puts a stress in this direction, for example. And if you then rotate your magnetic field, you can rotate the stress vector. And of course, it's then quite straightforward to say, okay, I want to do this faster and faster, and therefore I'm making now use of this dynamic magnetization vector, and I can therefore connect the precession of the magnetization to this rotation of this elastic stress vector in my my film, and therefore create my phonons. We have not, in addition to talk about the phononic system, and for us, it's typically a magnetic thin film on top of a crystalline substrate. The crystal will have some properties. However, this D is thin and the L is large, so we will be dominated by the phononic properties, crudely speaking, of this substrate. And if you look at this, you are basically can characterize or find the analogy of this so-called bulk acoustic resonators or bulk acoustic shear wave resonators with a Fabry-Perot resonator. The wavelengths are typically small compared to the extent of L, and therefore you will see a comb-like pattern if you tune the frequency. And here you basically have a constructive, given by the boundary conditions, a constructive interference and a standing wave phonon here in this layer stack. This free spectral range, which denotes the separation between these two comb structures, is linked to the sound velocity and the geometry of the system, and you can identify the resonance frequency as the overtones of this system. If you now go in the direction of what would I expect, what would be the prototypical signature of a magnetization connecting to this acoustic resonator, this is an assumption when I'm looking at the microwave spectroscopy, so I'm looking at the magnetization dynamics using microwave spectroscopy, then you would expect the following signature. You would expect a ferromagnetic resonance with a slope which is given by a G factor or anisotropies, etc. And then they interact with a phonon, with a standing bulk acoustic wave resonator excitation, which is magnetic field independent, which runs in this white dashed line, and you see some form of anti-crossing. So this is the signature that you would love and expect. And then you start experimenting, and we have learned already that the obvious choice is to go for low line widths, because then you need less coupling in order to see strong coupling effects. And this brings you typically to yttrium iron garnet. If you look at the ferromagnetic resonance, this is, I think, a nice example for a Kittel mode for an out-of-plane ferromagnetic resonance of a YIG film of 600 nanometer or so. And you see this diagonal line. So this is your Kittel mode. And you see nothing there, so it's of your Magnon-phonon. And Richard Schlitz, who is working presently in the Gunwein group, he made out that and this was already clear from work from Olivier Klein, that you need to focus here on a small spot, because the frequencies at play for this mechanical overtones, they're quite densely packed. So for this situation, so the layer stack is roughly 600 micron or so, or 550 microns. You end up with the following. You have yttrium iron garnet, which is your low damping material on GGG. You look at this and you see that there's a slight distortion here of your microwave resonance, kind of modifying your Kittel mode by this kind of intercept. And then here's the next one. And these are frequency periodic, so you start to identify this with the free spectral range of your mechanical resonator, and you plug in the numbers, and this corresponds well to GGG. And you start analyzing this in terms of coupling rates and damping rates, similar to what we discussed. And the procedure is roughly as follows. You take your spectroscopy data as function of the frequency. So you take here in this spectrum a vertical cut, and then you will find out that there is kind of a broad envelope which is associated with the damping of the ferromagnetic resonance, and there are kind of these peak structures. You could call this an equivalent of an transparency effect or an additional absorption effect. And then you basically, your task is to analyze this broad structure, this peak structures here, in order to figure out all the parameters. This was work in collaboration with Gerrit Bauer's group. And in principle, the procedure is you determine here the envelope function. You go to an off-resonance situation where the disturbance of your FMR mode on the mechanical properties is reduced. Then you can fit here the line width of the phonons, and the Magnon-phonon coupling is basically encoded in the depth of this dip here. And you can then do this analysis very carefully as function of frequency and find basically that you have a decent yttrium iron garnet film with a reasonable Gilbert damping. There's a slight increase in the phonon damping with frequency. Then you see some lobe structure in the coupling between the phonons and the magnons, which originates from the fact that you need to consider the mode overlap. So you will always be able to excite the fundamental mode, the Kittel mode, in your magnetic system, and then you need to match the nodes or the phonon mode shape in the GGG and in the YIG in order to launch efficiently phonons into the system. This was nice, but actually we wanted to look for different substrate materials. Yttrium iron garnet, GGG, the go-to substrate for yttrium iron garnet, the gadolinium gallium garnet, it behaves complex at lower temperatures, and we thought about, is there any way to combine this in a more integrated fashion with superconducting circuits, for example, and then silicon or sapphire are the go-to substrates. Unfortunately, yttrium iron garnet does not grow naturally on silicon or sapphire. And then you're hunting for the next best candidates, and we chose cobalt iron because it's known as a metallic glow damping material. So this is our parameters for the cobalt iron. The alpha is a factor of 10 worse than the yttrium iron garnet that we had already. Otherwise, it's doing not so bad, I would say, and is therefore ideally suited for our experiments. I want to kind of move to the next step, and the next step is to think about a little about the crystalline structures. So for sapphire, you have a hexagonal symmetry, and what we considered is propagation along the z-axis. For the z-axis, so this was for the motivation of angular momentum transport. The slow shear wave and the fast shear wave are degenerate in frequency, and the longitudinal velocity is kind of far off. This should allow you to transport phonons in a circularly polarized manner along the z-axis. If you're more into phononic birefringence, then my recommendation is to go somewhere in an angle which utilizes that you have here different velocities. Silicon, you could also do silicon. Silicon has a different symmetry. It's cubic. Therefore, there are kind of different symmetry points here along the principal axis. You have a degeneracy in the shear wave velocities. You can do a small angle approximation. So the degeneracy is true for 0 angle for perfect propagation along the z-axis, or perfect propagation here along one of the a-axis. If you tilt away slightly, then you will notice is basically the short answer. So what do you observe now is we have here again the ferromagnetic resonance, and now we saw something initially puzzling. So we have these double features, and these are again frequency periodic, and we start to analyze this in a similar fashion as we've seen before. We actually took various frequencies, so which you see here, and we see that the separation between these two kinks, they increase. And actually, this is expected, and I hinted to this already, because we have slightly different shear wave velocities for the two transverse shear waves, and we can understand this frequency difference in terms of the so-called miscut in the crystalline in the crystal. So the message is, if you want to do transport or phonon angular momentum transport with phonons, then please keep this in mind. This is particularly worrisome when your damping rates, your acoustic damping rates are narrow, because then they would decouple, and then you would also be able to excite only a linearly polarized elastic waves. The good news is that this is a positive side for a phononic birefringence, because this tells you that you can actually engineer this, and one needs to consider which kind of propagation direction is favored in order to realize a phononic birefringence device, so to say. Does it only work on silicon and sapphire? No, the messages you can do actually a lot. We tried out GGG, which performs little worse. Silicon performs acoustically very nice. So you see here a line width analysis of the FMR line width. So you see the small peaks, the tried A-plane sapphire, and then we try to walk in the footsteps of the Klein group to transfer magnetic excitations from cobalt iron to cobalt iron on the opposing side of the sample. And one of the signatures that you expect, or that are predicted to demonstrate this, is the alternating amplitude here that we observed. You can ask yourself, so I showed you data from room temperature for the cobalt iron from low temperatures, 5 Kelvin, how this evolves as function of temperature. You can do this. You will notice that the phonon frequencies, or the resonant frequencies of the bulk acoustic resonator vary with temperature. One part of it is that you have thermal expansion coefficient, and the other part is that the elastic properties change of the material. There are kind of there's nice physics, and then the damping certainly, and then also in the phonon damping, which you can recover from this data actually quite easily. I also want to present you two outlooks. So what is the kind of longer term vision? One is to, and this was an idea which is cooked up with Sylvia's group, to think about conversion from the microwave domain to the optical domain, with the motivation that this is one of the ingredients for long-range connection between quantum processing nodes. And one way of realizing this could be that we couple strongly the microwave resonator to a magnetic excitation, and this magnetic excitation to an elastic excitation. And we combine then this elastic excitation via physics of optomechanics to an optical signal. This is one way forward. And the other way forward we are presently looking into is to interrogate this coupled spin microwave cavity ensembles with squeezed microwave light. And so this is a first reconstruction of the quantum state which goes into this ensemble, and we are hoping to get more out of this. And with this, I'm just showing you my summary slide, and I hope you had fun with connecting quantum systems and learned something about potential signatures and potential applications. Thank you.
Thank you very much, Hans. So now we have things open for questions. If you please raise your hand, and I will open up and you can ask directly Hans your questions. Let me see, I would wait a second or two. Usually Elias or somebody else will ask a question. But let me start a little bit. Yeah. So now you've seen, particularly in the Magnon-phonon systems, you have this some of the issues that are coming up with damping, but always particularly thinking on the magnetic ferromagnetic systems. Yeah. How will you extend these things to the, or is it possible or feasible, and how would you think of doing it for compensated order?
So I think
higher frequencies of magnons and things like that.
So in principle, this is first and for all a technical issue, I would say. So there are, I told you that I'm preferring superconducting microwave resonators for basically the reasons that the technology is at hand. So if you switch to high frequency magnons, so I'm thinking in my head about 200 gigahertz, then the approach would be that you need to engineer your system correctly, in the sense that you need to build, for example, a cavity, a microwave cavity at 200 gigahertz. This has been done for electron spin resonance experiments. And then basically you need to understand and figure out the effective magnetic dipole that you have in these excitations and how this translates to an effective coupling range. So
in cases here, you have a linear dispersion typically for some of the systems rather than quadratic. So would that be a problem in terms of the phonons, the branches crossing, or not?
So I was talking about optical cavities. There I don't see any issue.
Okay, nice.
I think the go-to materials would be the typical fruit fly, like magnesium difluoride, which has extremely low line width. In the terms of acoustic resonances, I think in principle one need to carefully consider which phonon branches you can interact with and what kind of spectroscopy you would use for this. So I would naively think that I would opt for terahertz interrogation techniques and check if I can get a antiferromagnetic resonance interacting with the optical phonon branch, for example. With this, but this is more an intrinsic interaction, which I think lives or can live on the same footing.
And the thing that you showed in the outlook, when you look at coupling different cavities, so what is the thought in there that how would you do the effective coupling through being them connected on a substrate or?
So here, this example. So the idea is actually to have a device design which is inspired by optomechanical crystals. There's a lot of optomechanics works in the optical domain. And you can co-localize your acoustic and optical excitations by appropriately shaping the holes in this phononic crystal and this photonic crystal. And then the idea is to design this out of a magnetic material, for example, yttrium iron garnet, and connect here to the elastic properties of the yttrium iron garnet, and then couple this by an adjacent or microwave resonator in proximity to the microwave cavity. And this should, in principle, work for cavities according to our estimates in the gigahertz range, and then interrogated, for example, by 1550 nanometers.
Excellent. Libor, you have a question? Go ahead.
Yes. Thanks, Hans, for the beautiful talk. I wanted to ask about the previous slide when you has these beautiful couplings with the phonons.
This one? Or?
Are there any conditions on what phonons you have? So, for instance, if you would take, I don't know, it was in the last slide, in the Outlook slide.
This one?
Yeah, but any, there was the coupling to the phonons, and I was wondering whether you could see coupling also, or if people were studying couplings in systems like some layered cuprate, where you can have these weird buckling modes of phonons. If you could be sensitive to this as well, or no. Basically, what are the constraints on the phonons, which couple to the phonons?
I tell you what our constraints are, and then we could discuss maybe later on further what your thoughts are on this. So for us, it's helpful to have phonons or standing bulk acoustic waves with high quality factors, because then the signatures become eye-falling or easy to detect. That means that we are suffering basically, or we're taking a substrate which is polished on both sides to an optical grade, and then we are suffering that you have maybe not a perfect parallelicity of the two surfaces. That means that you're losing phonons to a side, so to say. I think there's a lot known in what I would call classical phononics in terms of also conversion of shear waves to longitudinal waves. I think that's worth looking into. But what we actually probe, or the phonons which we are actually interact in the sense of a dispersion relation, are you look at the dispersion relation, you look close to the gamma point for the acoustic phonons, and if you can create a substrate or a crystal of your choice, then you are in business, because you can form or try to form a resonator out of this crystal of interest. And then my view would be that you just use the ferromagnetic film in this case as a probe, which then interrogates the phononic properties of this otherwise undisturbed crystal. And then basically what we do here is we deduce the phononic properties of sapphire and silicon, which are well known, using this magnetic interrogation technique, so to say.
Thanks.
And you could do this with any crystal of any sorts. There are many ideas out there what kind of crystals could be interesting, what kind of cuts could be interesting in order to talk to specific selected shear waves.
Okay. Cool. Okay. So let's see. I think today it's just maybe the beginning that people are a little shyer. Maybe they're busy with other things. So
there was a break. People aren't used to it, Jairo, anymore, you know?
Used to every week, you know, everybody's asking questions. So I recommend that anybody that finds it interesting, of course, the ones that are watching it afterwards, as usual, contact Hans directly with any questions. And this very nice, fascinating cavity spin physics that he's leading. And with that, I think I'm going to turn off. In the other side is streaming. So end stream. End it in this.